from the Cambridge syllabus, here's what they expect. You should be able to show an understanding of binary magnitudes and the difference between the binary prefixes and decimal prefixes. So we're going to be looking at binary magnitudes, and then we got to understand the difference between Kibi and kilobyte, Mebi byte, megabyte, Kibi byte and gigabyte, Tebi byte and terabyte. So let's go ahead and get started. So binary numbers are represented as bits, zeros and ones. Each digit, the 1 or the 0, takes up 1 bit of space. Now in binary sign and magnitude, the leftmost bit represents the sign, with the remaining bits representing the binary value. So if the leftmost bit is a 0, we know we're dealing with a positive number. If the leftmost bit is a 1, we know we're dealing with a negative number. So let's look at an example using 8 bits. Let's take a look at another example. How about positive 68? So the plus sign tells us the leftmost bit must be a 0. The remaining 7 bits give us a calculation for 68. So I have a positive sign. This becomes a 0 because I'm dealing with a positive number. And then I need to get to 68. Will 64 help me get to 68? It sure will. And then all I'm left looking for is the number 4. Is this a 4? Nope. No. Here's my 4. And then my binary sign and magnitude binary number is 01, 000, 100. That will give me positive 68. Now, our second example would be great if it was a negative number. Here's one, negative 25. The negative sign tells us the leftmost bit must be a 1. The remaining 7 bits will give us a calculation for 25. Same chart here. I know right away because I have a negative sign, it's going to be a 1. Now I'm looking for the value of 25. I can't use 64. I can't use 32. I could use 16, or I need to use 16, which will get me 9 again. This should look very familiar. And then the 8 and the 1, which will get me to 9. 9 minus 8 is 1, and then 1 minus 1 is 0. Gets me all the way to 25. So that is our binary sign and magnitude for negative 25. The only difference is the sign. In the previous problem, we had a 0 indicating positive. This time we have a 1. The binary value of these 7 bits is exactly the same. We got to talk about why you don't want to use binary sign and magnitude. It can lead to a positive 0, and you may be saying, well, how in the world can you have a positive 0? What about a negative 0? Here's how you get a positive 0. We said, it's a positive 0. My sign would be a 0, and all of these would be 0. In binary sign and magnitude, that's a positive 0. For a negative 0, my binary value, are all zeros again, because I don't have any of these values, but it's a negative 0. That means my sign is a 1. That's how you can get a positive and negative 0. It's almost, there's a more efficient binary system that we'll be looking at in the next podcast. But Cambridge wants you to know how to use binary sign and magnitude. This is how you use it. It's that simple. You've probably heard these terms before, such as kilobyte, megabyte, gigabyte, terabyte. You might have heard those terms before, and you may be saying, okay, I know a little bit about those, or maybe you know what they are, or maybe you thought you knew what they were. But what about these terms? Have you ever heard these terms before? Because not many people are familiar with them. Kibi byte, Mebi byte, Kibi byte, Tebi byte. What about those terms? Well, what's the difference between them? So decimal prefixes are the ones that you're familiar with. So think about the prefix kilo. What does that mean? Most people will tell you that means 1,000. So a kilobyte isn't 1,024 bytes because it's a decimal prefix, not a binary prefix. So a kilobyte is technically 1,000 bytes. A megabyte is technically 1,000 kilobytes. A gigabyte is technically 1,000 megabytes. A terabyte is technically 1,000 gigabytes. Now the binary prefixes work a little different. So binary works off the power of 1,024. For example, I can take 2 to the power of something and get 1,024. I cannot take 2 to the power of something and get all these numbers specifically when I break it down to the amount of bytes or bits. So 8 bits make up a byte. A Kibi byte is 1,024 bytes, working off 2 to the power of 10. A Mebi byte is 1,024 Kibi bytes, working off 2 to the power of 20. A Kibi byte is 1024 Mebi bytes, working off 2 to the power of 30. A tebibyte is 1024 gigabytes, 2 to the power of 40. So when people use these term megabytes, you're not really sure if they're using the correct term or if they're not. And here is why. Just remember before we move on, computers deal with these things in binary because you can get exact measurements with the power of 2 when we're talking about. So we can use 16 different characters for each group of 4 bits that we have. Now we use the numbers 0 to 9, which is the first 10 characters, and the letters A to F, which are the last 6. Now you might be saying, why would you use letters? Well, A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. Now you might be saying, we just talked about using 16. Why do you stop at F? Don't forget that 0 is a number too.
So for the sake of time, I'm just going to do an example myself because it takes him like 10 minutes to get through his. I'll be using the number 46. 46 represented in binary is this. I'm not going to walk through the binary to denary conversion because you should already know that. So to convert into hexadecimal, we gotta split this into 2 groups of 4 bits, which some of your teachers might call a nibble. So first, let's work on this group. And we'll add the powers of 2 because you're not Jesus or the Buddha or the God of whatever religion you believe in. So we just add up these 3 values and we get, what, 14? And then here we don't even need to do the other 2, it's just 1 and 2. So 2. But we're not done. We still need to convert 14 into its hexadecimal value. 2, it's fine. We already finished that. So what we need to do is we need to convert it into a letter. And for that, we can just write the chart. So here we could see what letter corresponds to 14, and we could just choose that. So here it would be E. Well, I mean, every time 14 appears, it's E, but it's E. 14 is E. So yeah, that's how you do it.
There are only a certain amount of addition possibilities you can get when you're doing binary arithmetic. And as long as you remember these rules, you'll never go wrong. So the first rule is very easy. 0 plus 0, and that equals 0. When I have a value of 0, and I add a value of 0, I get 0. The next one is 0 plus 1, and that's going to come out to 1. Any value added to 0 will always be the value itself, and you can have the opposite of that. 1 plus 0 still equals 1, and then you have 1 plus 1, which often throws students off. And what happens here is you get a 0, and then you carry the 1 to the next column and you bring it down. Now, when you're looking at the binary value of 1, 0, that is the value of 2. When you're looking at the binary value of just 1, that is 1. What is 1 plus 1? 2. But in binary arithmetics, we can't write the letter 2. That would be the decimal system or the denary value. We have to write the binary value, which is 1, 0. There are 2 bits here. The first bit representing 1, which we don't have. The second bit representing 2, which we do have. The third possibility you can get is 1 plus 1, and then with a carry of 1 from a previous column. So you can have 3 ones here. 1 plus 1 plus 1. Well, that is going to equal 1, and then I'm going to carry the 1 over, and I'm going to bring it down in the next column. When I look at here, this is the value of 1. This is the value of 1. What is 1 plus 1 plus 1? It is 3. This is the binary value of the representation of 3. This would be the value of 1, which I do have indicated by the binary 1. And this is the value of 2, which I have indicated by the binary of 1. 1 plus 2 equals 3. As long as you remember those rules, you can't go wrong. Alright, so let's jump into it. So we have this practice problem, 7 plus 5. It's already been written into binary for us. So what we're going to do is we're going to run through these columns. And we're going to reference back to the rules. So I have 1 plus 1. That means we're going to have a 0, and I'm simply going to carry the 1. So then I have 1 plus 1 again, because it's 0, we don't really need to count, there's nothing there. So I have 1 plus 1. When I have 1 plus 1, I have the same thing. I put a 0, I carry the 1. Now we have 3 ones in a row, which means I'm going to bring down a 1, and then I'm going to carry the 1, and then we have 1 plus 0. When we have 1 plus 0, anything added to 0 is always going to be itself, not carrying anything this time, and then we have 0 plus 0, which is 0. Now 7 plus 5, doing mental math, equals 12. And we're starting off with a simple problem just so you can see how this works. Now because this is Cambridge and we're working with 2's complement, you need to make sure that your leading number, because it's positive, starts with a 0. That's very, very important. So then we write out our values here: 1, 2, 4, 8, and then negative 16. Because remember, in 2's complement, the leftmost bit is negative. So I don't have a negative 16. I have 8 and 4, and 8 plus 4 equals 12. So we know that this answer is correct. All right, let's move on to another one. 95 minus 68. What do we do with an extra bit? So in this one, if I planned correctly, we should wind up with an extra bit. So what I'm going to do is 1, 2, 4, 8, 16, 32, 64, 128. I'll move this back so we can see it. And then this is a negative 128. I want to forget that because we are working in 2's complement. So this can be read, we said this can be read 2 different ways: 95 minus 68 or 95 plus negative 68. And we're going to read this as 95 plus negative 68. This minus sign goes with the 68. So we're actually combining 95 and we're combining negative 68. Let's start with 95. I don't need a negative 128. I do need a 64. And 95 minus 64 is going to be 31. Can't use a 32. I can use a 16, and that comes out to 15. I can use an 8, and that's going to come out to 7. I can use a 4, which will get me to a 3, and that means these two need to be filled out, and that is positive 95. Now we got to look at negative 168. So I'm going to erase this so I can get some room. Well, it's not erasing, but, well, that's okay. We'll just make some room somewhere else. So again, we're not working with this. Now we're working with negative 68. I definitely need a 1, and the reason I need a 1 is because it's a negative number. So I have negative 128. I can't use 64. That will get me to negative 64. I need to be able to get to negative 68. So I don't need a 64. I can use a 32, and that of course will get me to negative 96. And then I'm trying to get to negative 68. I need a 16. So I'm going to add on 16. That comes out to 80. Then I can use an 8. That will get me to negative 72. And then I need a 4. And that will get me to negative 68, which means these can be 0. Now that I have all this written out, I can do my binary arithmetic. What's 1 plus 0? 1. What's 1 plus 0? 1. What's plus 1? 1 plus 1, remember, is going to be a 0, and we carry the 1. What's 1 plus 1 plus 1? This time, instead of a 0 carrying the 1, it's going to be a 1 carrying a 1. And now I have 3 1s again. That's going to be a 1 carrying a 1. I have 2 1s, which is going to be a 0 and a 1. I have 2 1s. It's going to be a 0 and a 1. Perfect. And we are going to get the carry bit. We have a 0, but now I can't carry the extra 1. Well, that's okay. And here's why that's okay. When we're looking at 95 minus 68, and this is because we're working with 2's complement. When I look at 95 minus 68, I know I need a positive answer because I know 95 is greater than 68. If I carry that additional 1 and had it, it would say, hey, that's a negative number. Well, we don't have a negative number. We have a positive number. And what must our positive number must be? Or what must it start with? It must start with the 0. Now let's work out this 95 minus 68 and see if it works. So let's write our values above here. 1, 2, 4, 8, 16, 32, 64, negative 128. So we have a 16, we have an 8, that is 24, plus 2 is 26. So we have 26, and when we're looking, and then plus 1 more, got to add that other one, which is 27. So we added the 16, the 8, the 2, and then the 1. 16 plus 8 is 24, plus 2 is 26, plus the 1 is 27. What is 95 minus 68? 95 minus 68 is positive 27. So even though we didn't carry this extra bit over, that's okay. We don't need it because we're working with 2's complement. Now that's not always going to be the case. And let's take a look at an example where it's not always the case. So this time we're going to do 82 plus 69. I'm going to do the same thing I've been doing. I'm going to write in these values, and it does not take long to write in the values. You don't want to be lazy. Trying to do it in your head, you could make a very, very simple mistake, and we have all done it. We've all tried to save, I don't know, about 15, 30 seconds of our life trying to save time, and really 13 or 15, 30 seconds isn't really that big of a deal. It really will make sure you get the right answer. When you take your Cambridge exam, these are questions you should get right. So I know I have 2 positive numbers here. Both of these are going to be 0. Now, 64 for, let's start with 82. I need the 64 to help get me to 82. 12 minus 4 is 8, and then this becomes 7. We have 18. To get 18, I don't need a 32, I need a 16, which will leave me 2 left over, and that is right there. So that is my binary number for positive 82. It all works out. Now for 69, I need 64, which leaves me 5, which is 4, and 1. 4 plus 1 is 5. So that will be my binary number for 69. So all I need to do now is follow the arithmetic rules. So let's go ahead and follow our arithmetic rules. We have 0 plus 1, which is 1. 1 plus 0, which is 1. 0 plus 1, which is 1. 0 plus 0, which is 0. 1 plus 0, which is 1. 0 plus 0, which is 0. 1 plus 1, which is a 0. We carry the 1. And 1 plus 0 is 1. So 82 plus 69 is, let's see here, that would be 151, I believe. I'm pretty sure it is. Let's go ahead and do some simple math. 9 plus 6, yeah, 151. We have a huge, huge problem. And that is right here. That is right here. In 2's complement, this says it should be a negative number. That is a big problem. And the reason it's a big problem is because when we work this out, we see that it does not come out to 151. It doesn't come out anywhere close to that. So, and then 7, 4 plus 2 plus 1 equals 7. That's where I'm getting that 7 from. So let's see here. 8 minus 6 is 2. Let's just do this one at a time. Make it a lot easier. So, and then we're going to add that 7, and that's negative 105. We know negative 105 is not even remotely the same as 151. What has happened inside this binary arithmetic is what we call overflow. And the reason there is an overflow is because the maximum value that I can get with 8 bits in 2's complement, the highest I can get is 127. In this video, we're going to take a look at images and calculating the file size for images. So let's go ahead and dive right in. By knowing some simple vocab, we can be prepared to tackle those questions. The first one is pixel. Now this is the smallest unit of an image. We can't be breaking it down any further than a pixel. That's the furthest we can break an image down. We also need to know image resolution. This is the total amount of pixels that make up an image. Simply find the area of pixels, count the length, multiply it by the width, and you get the area of the pixels that you need to answer the question. Now, bit depth. This can be a little tricky at first, so I'm going to make it as clear as possible and easy to understand. It is how many bits each pixel takes up or requires. Now, it directly impacts the amount of colors available per pixel, and that brings us to the word color depth. This is how many colors are available for each pixel, and that is dependent solely upon the bit depth. These two are related, and we'll take a look in just a few moments at exactly how they are related. Now, the formula for calculating file size is simply image resolution, the total amount of pixels, times the bit depth, which determines how many colors there are. So let's go ahead and let's take a look at a past exam question. So the finished logo is 500 pixels by 1000 pixels. Perfect. And now I'm going to multiply those two numbers together. All I need is the bit depth, and uses 35 different colors. Estimate the file size for the logo. Give your answer in kilobytes, show you're working. I don't see bit depth here. So we have 35 colors, but how many bits do we need for that? And how are we supposed to figure that out? With a simple formula where 2 to the power of x equals the amount of colors. Now that is where x is represented as the bit depth. Now you may be saying, well, okay, but 2 to the power of x doesn't have a whole number that equals 35. What in the world am I supposed to do? Are we supposed to do 2 to the power of, 4 point something, 5 point something until we get to 35? You don't have to do that. It doesn't have to come out to exactly 35. Let's work it out. 2 to the power of 1. That gives me 2 colors with a bit depth of 1. 2 to the power of 2. That gives me 4 colors with a bit depth of 2. I keep going. 2 to the power of 3. That gives me 8 colors with a bit depth of 3. 2 with a bit depth of 4 gives me 16 colors. That's not enough for 35 colors. Bit depth of 5 gives me 32 colors. That is not 35 colors. So I simply keep going to the next one. A bit depth of 6 will give me 64 colors, which is enough. So each pixel can have at least 35 colors. So now that I know that, I can answer this question. So I know my bit depth is 6. I know my formula is image resolution times bit depth. So I'm going to do 500 times 1000. It gives me 500,000 pixels. All I need to do is multiply it by 6. That gives me 3 million bits. Well, I need to go from bits to bytes, and then bytes to kilobytes. So 3 million bits divided by 8, that gives me 375,000 bytes. It wants the answer in kilobytes though, so I'm going to divide that by 1000, and my answer is 375 kilobytes. Just like that, I just picked up 4 points out of 75 on my paper 1 exam. Let's take a look at another one. A company is designing a website. The company creates a 4-color bitmap image for the website as shown. I'm going to pause right there and I'm going to say, you know what? I need 4 colors. I'm going to start calculating the bit depth because I'm going to need to know that. So off to the side, I start calculating that. 2 to the power of 1 is 2 colors. 2 to the power of 2, that gives me 4 colors. I now know the bit depth, and that answers A part 1. State the minimum number of bits needed to represent each pixel. 2 bits are required. Now that I know that, I can calculate the minimum file size. I count the pixels, 1, 2, 3, 4, 5, 6. I count them vertically, 1, 2, 3, 4, 5, 6. So I know there's 36 pixels. 36 times 2, the bit depth, gives me 72 bits. When you do 72 divided by 8, my answer is 9 bytes. Now, if you leave it at 72 bits, because it doesn't tell us what we have to convert it to, 72 bits or 9 bytes, both of these would be acceptable. And we just picked up 4 out of 75 points on this exam. So file compression. Now, sometimes a file needs to be compressed, and this means reducing the size. When we're talking about compressing a file, we're reducing the size. Now, reducing the size can save storage space on our own device. It can also reduce the amount of time needed to transmit the data or stream the data from one device to another. MP3 files, those are compressed audio files, and something that everybody's very familiar with. If they were not compressed, they would be much larger and you wouldn't be able to fit as many songs on an MP3 CD. MP4 videos, those are compressed videos, and those are simply multimedia files. And there's 2 types of compression that are commonly used. The first one is lossless, and the second one is lossy. So let's go ahead and continue and take a look at some lossy compression. So here we have 2 sound files, and we just got done talking about MP3s versus the original format it's in. The original format that it's in is a WAV file, which is on the right hand side right over here. On the left hand side, it's an MP3 file. And you can see the size difference is huge. In the original file, we have 45.8 megabytes, so almost 50 megabytes. Here, right over 6. So for this Volbeat song, Lola Montez, we can see that when we use an MP3, we have it's compressed way down. It doesn't take nearly as much storage space as possible, and the MP3 sounds pretty close to the actual file, and we'll talk more about that later. So Lossless compression, let's talk about that. Now, all data from the original uncompressed file can be recreated once it's uncompressed. This is important for files that cannot lose any data. So we're not losing any data here. Think of a Word document. You cannot lose any characters from the Word document. Imagine you're typing a term paper and you just lose characters from your term paper. It's going to look like a set of random letters. What about a spreadsheet showing savings or financial details? You wouldn't want to lose those either. Now, there is a form of lossless compression that's called run length encoding, and it is lossless compression. It's one form, and you can actually take large characters and shrink them down by saving space. All right, let's move on. Let's talk about compressing an image using run length encoding. Now, you can compress an image using lossless compression by employing run length encoding. Now, run length encoding is lossless compression. It's a form of lossless compression. You would only do this if it would be beneficial to use lossless compression over lossy. Now, in this example, white is represented by a binary value of 1, black is represented by 0, and we have the character F here. So if you look, you can see in this top row, we have all ones, then we have a white, followed by black, followed by another white, and that's what the second row shows. 1, 0, 0, 0, 0, 0, 0, and then 1. And then you can see here, these next two rows repeat, because we only had these shaded in. Now, when you look at the compressed RLE format, it can be a little confusing, but it isn't really. Having to write all this out can be very long. I make my students do this on a sheet of graph paper to understand how long it takes and how hard it is to read, because you can easily lose your place, especially if it's not the letter F, if it's an image that we can't tell. Now, for RLE format, we have 9W. What do you think that means? 9 whites, 6 blacks, 2 whites, 1 black, 7 whites, 1 black, and so on. And what we do here is we use 9-1. What does 1 refer to? 1 refers to white. We have 9 whites followed by 6 blacks. Now, if you're looking over here, you'll see there's 1, 2, 3, 4, 5, 6, 7, 8. You may be saying, well, hold on here. There's 8 whites, not 9. But it's not about just building one row at a time. How many whites do I have in a row? It says 9 whites followed by 6 black followed by 2 whites. So let's do that. Let's see if we get 9 whites. 1, 2, 3, 4, 5, 6, 7, 8. Now that row is done, you move to the next row, 9. That is where the 9 white is coming in, followed by 6 black. So we have, as soon as I get my mouse, 1, 2, 3, 4, 5, 6, followed by 2 whites. 1, done with this row, I go to the next and I continue my count. 2 whites, 1 black, 7 whites. 1, 2, 3, 4, 5, 6. Done with this row, and I go to 7. So when you're looking at the RLE format over here, you may be saying they made an error. No, they didn't. It's 9 whites in a row, and when you finish with 1 row, you immediately go to the next row. Okay, so let's talk about lossy compression for an image file. So these are 2 identical images, I should say. In an image file, you may not need the highest resolution. Now, the file is going to be close to the original, but it will take up less space by using lossy compression. Now, once the file is converted to JPEG, the JPEG will never be able to be converted back to the raw file, and that's because information has been lost in lossy compression. For example, the raw image, you can see in the sky, there are multiple colors here. When you're looking at the JPEG, some of that detail has been lost, but it's still an acceptable picture. Looking at this couch, you can see some, deep, darker colors than you can over here in the JPEG. This rug over here looks a lot different in the JPEG than it does the raw file, but we can still tell that there are buildings in the background. We have a couch, we have a rug, we have a table. We just have lost some of the detail because we don't need all the detail. So, and this is just citing my sources from picturecorrect.com. All right, vector graphics. They're defined in XML text files, which allows them to become compressed. Now, because it's a text file, we can say it is lossless, although most of the time vector graphics can be adjusted without losing quality. We talked about this with bitmap images. Bitmap images, when you stretch them out, they become distorted because the amount of pixels don't change. Vector graphics, we say that is a text file because it's defined in XML text files, and they're redrawn every time you enlarge them. So we say that would be lossless instead of lossy because you're not losing any of that data. All right, lossy compression for an audio file. Now, MP3 uses audio compression to convert sounds to MP3. This reduces the file size of a normal music file by about 90%. Now, in our Volbeat example, we saved right around 86%, which is still close to 90. Streaming MP3s will be much better than streaming the original file. Think about how long it would take to load 45 megabytes or, God forbid you're on a data cap. If you're streaming an album, you're going to be streaming gigs of music rather than megabytes of music or data. So you definitely want to use MP3s. Now, MP3 music quality will never match the sound file on an original CD, but it's satisfactory for most purposes. And this is done by what is known as perceptual music shaping. So here's what happens when they make an MP3. In perceptual music shaping, the frequencies that are outside the human hearing range, we simply remove them. So if there's some sounds that we cannot hear, they just take it out. Well, when you're taking information out, that is going to reduce the file size. If two sounds are played at the same time, but only the latter one can be heard by a human, they're going to take the other one out because it can't be heard. When you're taking information out, it's going to be reducing the file size. Now, it's important to note that bitrate can increase the quality or decrease the quality of an MP3. For example, a 56 kilobits per second quality versus 320, you're going to have a noticeable difference. And we're going to take a look at that in class with an exercise. I've had a few students say that they're able to tell the difference between 320 and 128, and that's what a standard MP3 is 128, usually tops around 320. I've had several students say, oh, I can tell the difference, and out of all the students who have come through my class, only 2 have been able to do it at the time of this recording. So let's take a look at a graph to see how we actually lose sounds for an audio file. So, for example, this was our original audio file, this red line, and say we want to take it down to 2 bits. Well, notice the sharp increase here. I don't have this gradual increase. My blue line is what I have to use, and you can see the sudden decreases here based on the bit information, the digital information. I lose this gradual upswing. I lose this gradual downplay. Like right here, it just suddenly drops. And then it goes over. Here, the pitch suddenly drops. And right here, it suddenly drops. So we're losing all that information just by doing 2 bits. Now, let's talk about general compression overall. There are some general methods of compression without needing lossy or lossless compression. For movie compression, for example, we don't use lossless or lossy. We're going to use movies, and here's how we do it. They reduce the sampling rate, they reduce the sampling resolution, and they reduce the frame rate. By taking data out, you are lowering the size of the movie. For an image files, well, we crop images, we decrease the color bit or depth, and we decrease the image resolution, so we still get an acceptable quality picture, but it's not the same. Now, once you compress a movie into the image files, you're not going to get the original back. For example, there are DVDs. DVDs are compressed sound and video. When you get a Blu-ray, that is uncompressed video and uncompressed sound, and that's why Blu-ray is considered better than DVD. Blu-rays are uncompressed, DVDs are nicer than VHS, but they're still compressed. So we have thick clients and we have thin clients. We know that they're associated with the client-server model, but what is the difference between them? We need to know what they are, and by knowing what they are, we can also hit that learning target for the difference between them. So let's start with thick clients. A thick client can either be a device or software, because remember, it refers to both hardware and software, and it can work either online, but it also can work offline. Now, if it's offline, it can still do some processing without being connected to the server. When it's connected, it can be connected by a LAN, WAN, or MAN, a virtual network, the internet, or even a cloud computing server. Now, hardware examples is a normal computer, your PC, your laptop, tablet, whatever it may be, because it has its own storage. Hard disk drive, solid state drive, RAM, operating system, and this means it can operate both online and offline. A game like Monster Hunter World is an example of a software one. It can run independently on a user's PS4, but it can also connect to the Monster Hunter World online servers to play with other gamers. So that would be an example of a thick client. Now, thin clients. Unlike thick clients, thin clients rely heavily on access to a server to allow constant access to files and to allow applications to keep running. Thin clients do not work unless they're connected at all times to a computer or server. Now, like thick clients, it can be a device or software, so it can be a hardware device or it can be software. Now, regardless whether it's a software or a hardware device, it must be connected to a powerful computer for processing to occur. Now, the processing can be done by a server on the internet or can actually be part of the LAN, WAN, or MAN, the local area network, the wide area network, or the metropolitan area network. Now, a web browser has limited function on its own. You connect it to a server and it can do a lot. That's a software example. You open up Chrome, there's very little it can do. But if you connect it to the World Wide Web or a server, you can do a lot more with it. You can view web pages. But if you're not connected online, the browser is not going to be able to do anything for you. It's very limited in what it can do. Now, a hardware example is like a cash register where you check out your items. It needs constant access to find the prices, handle the transactions by customers, and do any significant processing. When you ring up an item, it doesn't magically know how much it costs. It's looking up that item in the database. Well, it has to be connected to that. That is what a thin client is. Okay, so let's dig into topologies. This is where the bulk of the lesson is going to be today, because there's nothing more about thick and thin clients that we need to know. So these are the topologies you should be familiar with. This is straight off the learning targets. The bus network or the bus topology, the star network or the star topology, a mesh network or mesh topology, the hybrid network or the hybrid topology. So what do we mean when we say a topology? It is how computers are connected to make complex networks. And the first one is a bus network. And there's a slight error in the picture here. We have all these computers that are connected to what we call a bus line. It is called a bus line because it is a straight line that all the computers are connected to. It doesn't have to be just computers. We can also connect printers to the bus line. We can also connect file servers to the bus line. Now, the slight error in the picture I've already fixed. With the bus network, it is important that you understand that there are terminals on each end of the bus line, and this is to terminate the signal so it's not bouncing back and forth repeatedly. For example, if we didn't have these terminals here, what's going to happen is as soon as the line becomes busy, the signal is just going to bounce back and forth on the bus line, and when it does that, it's going to say it's busy and nobody is going to be able to send any information to any other computers. So let's talk a little more about the bus network and make sense of this picture. So it uses a single central cable to which all computers and devices are connected. Little cabling is required and it's easy to expand. If you have room on the cable, you can add a device. Now, data can only travel in one direction, and if data is being sent, then other devices cannot transmit data. So if we did not have those terminators on the end of the bus line, whoever sends the first message, it'll do that infinitely until we either disconnect all the systems and shut it off and restart it, but that's not beneficial at all. We don't want it to just bounce around back and forth. Now, at each end of the cable, terminators, which we just talked about, are needed to prevent signal reflection, causing the signal to bounce back. Now, these are considered to be part of the peer-to-peer model. There is no network they're connected to. They're connected to each other indirectly through the bus line. And that brings some advantages. If one node fails, remember a node, we said from peer-to-peer, the remainder of the network can continue to function. So if we have 5 computers connected to the bus line, the main line, and one goes down, who cares? We can keep going. It's not going to shut down the entire company. We can increase the size by adding additional nodes easily by connecting them to the main line. I don't need to run all kinds of new line. We have that main line that we can use. Each node has an address, and when data is sent, each node looks at the packet and the address of the recipient. If it matches, it takes the data. If not, it ignores it. Now, packets are just pieces of data. When you send data, it's split up into packets. You can think of messages or data and little envelopes that have an address on them. If it matches the address, it says, hey, that goes to me. It then pulls it in and it takes it. Now, bus networks are great for situations with a small number of devices with light traffic, such as a small company or office. And when you have advantages, you also have disadvantages. So unfortunately, there are some major disadvantages when you are talking about a bus topology or a bus network. If that main cable goes out, the whole network goes down. It's going to affect every computer because now they cannot communicate with who they need to communicate with. Under heavy loading, there is severe performance deterioration. It's going to slow way down. The network is considered not secure, and the packets being sent pass through every single node. That means it's available to everybody, and everybody can see it. So we looked at a picture of a bus topology. This is a correct picture, and you can see here they have the terminators on each end. If you have to draw a bus topology, you're going to draw your main line, you're going to draw some devices connected to it. That will be worth 1 point. Your second point is going to come from putting terminators on each end. They are usually done with circles or straight lines. If I were you, what I would do is indicate at the end what you have drawn by simply writing the word terminator on one end, or you can do what they've done here and write it on both ends. So that's it for a bus network. Now, let's talk about a star network. Over here, you'll see this is in a star pattern. It does not have to be in a star pattern. Over here, we have a 3x3 pattern or a 3x3 grid. Every device is going to be connected to a hub, or it's going to be connected to a switch. So let's start talking about this star network or the star topology. It uses a central hub or switch, and each computer or device is connected to the hub or the switch. Now, the hub or switch is known as the central node, and we'll get more into hubs and switches later. But real quick, a hub broadcasts the data to every computer. The switches broadcast it to a specific computer. Now, if you're in my class, when you come to class, we'll be taking a look at a switch and how it works specifically. Data being sent from a computer goes through the central node. It goes through that hub or the switch. Now, each computer has its own dedicated connection to the central node, and any type of network cable can be used for the connection. Star networks are considered to be a client-server model because they are connected to that central connector, the central node. That client is connecting to that server. So that's why they call it the client-server model. And it has some advantages. Data collisions are greatly reduced to how it's laid out, unlike the bus network. The bus network, data messages can collide. If two people are sending data at the same time, those messages can collide with one another, and we'll talk more about that in class. It's more secure than bus topology, since security methods can be applied to the central node, and packets will only travel to nodes with the correct address. It's improved by simply installing an upgraded hub. If one connection is broken, it doesn't matter. It only affects that node because each individual node is connected. Star networks are suited for evolving networks where devices are constantly added or removed. It's great to use where heavy traffic is being used because they're all indirectly connected because they're connected to that central node. And just like we said with bus advantages come disadvantages, the star network, star topology also comes with disadvantages. Now, if the central node, the hub, or the switch fails, it's over for the network. The whole thing is going down. It's going to affect every single computer, and the startup cost for this type of network is going to be very, very high. You have to buy the hub or the switch. You got to buy a cable for every single computer. You got to run that to actually connect them to the hub or switch. All right, let's keep moving on to the mesh network. So this is an example of the mesh network, and to understand this picture better, we can talk about it. Please feel free to rewind it and look at it after we talk about what a mesh network is, the advantages and disadvantages. So there are two types of mesh networks, and they are called routing and flooding. Now, routing mesh networks works by giving the nodes routing logic. So they act like a router. Data is directed to its destination by the shortest route and can be rerouted if a node fails. And we call that packet switching in A level. We call that packet switching. Now, flooding, on the other hand, sends data through all the nodes using no routing logic. Now, this leads to unnecessarily loading the network because it's going, if there's a path open, it's taking it regardless of whether it needs to be used or not. It literally floods the entire network. It's considered peer-to-peer, but it is different than your standard peer-to-peer. These are used in medical monitoring of patients in a hospital where electronics are interconnected, such as a lot of DVD players or large screen TVs, and even modern vehicles where the network technology enables the monitoring and control of many of the components in the vehicle. So you can have interconnected lots of DVD players all playing the same thing, lots of electronics, large screen TVs all playing the same thing. So they're all connected to a network. So it's peer-to-peer, but slightly different. Now, there are advantages with a mesh network. It's easy to identify where faults on the network have occurred. Now, when we talk about a fault, we mean where computers have lost connection. Any broken links on the network do not affect the other nodes. There's good privacy and security since packets travel along dedicated routes. It's not visiting every single node unless you're using a flooding topology. The network is very easy to expand. The internet and the wide area networks, the metropolitan area networks, they're a typical use of mesh networks. You're going to do this on a much larger scale. You would not do this in a small office. You'd either go with the star topology or bus topology. When you're starting to get very, very wide, you're starting to look at a mesh network. And it has advantages, also has disadvantages. A large amount of cabling is needed. This means more money and time to run and lay all the cable. The setup and maintenance is difficult and complex because you have so many things connected. All right, let's keep rolling, talking about a hybrid network. So here we have a star network. Here we have a ring network, which you don't need to know. All you need to know is that each one is connected to the preceding one. And then we have a topology down here. So with a star network, you'll notice all these are connected together. So here we have a central hub. This computer is connected to this hub and also this bus line. So this bus line runs through to this computer, which connects to this hub, which will connect to every computer. Now down here, because we have a bus line, we call this a bus network. Notice it is missing a terminator here. So you would need to draw a terminator on the end of this bus line. There's so many pictures out there that don't include the terminators. You have to remember that bus lines must include a terminator. All right, so we put on that terminator. Let's talk about a hybrid network. It's a mixture of two or more different topologies. An example would be a network using a bus and star or bus and mesh, etc. It's two or more. They can be very complex to install, to configure and maintain, and it all depends on which type of networks make up the hybrid network. Now, some advantages though are they can handle large volumes of traffic. It's easy to identify where a network fault has occurred, and they are very well suited to the creation of larger networks. So here would be a hybrid network example. Imagine there are 3 local grocery stores independently owned and operated. We'll simply call them grocery store A, B, and C. Now, A uses a bus network topology, B uses a star network topology, C uses a mesh network topology. Now, A, B, and C, because they're independently owned and operated, they're bought out by a large company, and now that company wants to connect the systems of A, B, and C. Having to come in and redo all of that would cost just a huge amount of money. They don't want to do that. They just say, okay, how can we connect A, B, and C together? They already have a topology. How can we make it a hybrid? Well, they can be connected through the use of a hybrid system, even though they're all running different networks. You don't have to switch everything over to the same network, because a hybrid network uses 2 or more types of topologies. The connections can also be expanded easily without affecting any of the existing grocery stores on the network. So when they're bought out, there's no need to redo everything. So that handles the topologies. Now, the gates in this video are going to include AND gates, OR gates, XOR gates, NOT gates, NOR gates, and NAND gates. We're going to go over all of them. And we're going to start with the AND gates. So we said you need to know the symbol, and here's my symbol right here. Looks like a D shape. We have 2 inputs. We have input A and we have input B that results in an output. In this case, it is Z. It doesn't have to be Z. Some workbooks use X, some use different letters. It doesn't really matter what the output is going to be. It doesn't have to be Z. Inputs don't have to be A and B. Usually when there's 2 inputs, they use the letters A, B. When there's 3 inputs, they use the letters A, B, and C. And when there's 4 inputs, they use A, B, C, and D. Now, an AND gate will show a true value if both inputs are true. That means they both have to be 1. So for the remainder of this video, we're going to be using input A and B. So here's our truth table for an AND gate, and what we need to do is we need to fill out this output. And right here it says if both inputs are true. Here A is not true, it's off. B is also off. That's going to result in a state of being 0. Here A is not true, B is true, but that's not both of them. That's going to result in a 0. Here A is true, but B is not. That's going to result in a 0. Finally, in this last column, A is true, B is true. Both of them are true because A and B are true. That will result in a value of 1, it being on or true, in a state of being true. Our next gate is the OR gate, and we see once again we have 2 inputs and we have an output. Our symbol is a little different. It doesn't look like a D, it looks more like a Star Trek symbol that's been turned sideways. So an OR gate will show a true value if one of the following conditions are true. If one input, A or B, is true, as long as one of them is true, or both inputs are true. Now you may be saying that's not what OR means. There's a different special type of gate where one or the other has to be true, which we're going to go over next actually. So here's our truth table for our for an OR gate. So here A or B has to be true. Neither one of these are true, so that results in it still being off. Here A is not true, but B is. So A or B is true, so that results in a 1. Here, same thing. This time A is active, B is not. That results in a 1. Here, they're both active. That results in a 1. Our next gate is a XOR gate. So we have 2 inputs and we have our output. Now in the last segment, if you were looking at it a few seconds ago and you're saying, oh, well, A and B, that's not OR. That's where XOR gates come into play. Now, a XOR gate is an exceptional OR gate, and that's why the X is there. It really means it's an exceptional OR gate. It will only show a true value if one of the inputs is true, not both, like an OR gate. Only one of them can be true. So here's our truth table for a XOR gate. Here, neither one of them are true. That results in a 0. Here, only one is in a true state, or only one switch is on. That is B. That's okay. That will result in a 1. Vice versa here, this time A is on, B is off. That will result in a 1. Here, it's not one or the other. Both of them are true, and with an exceptional OR gate, only one can be true. And that's why I wrote 1 here. Keep thinking only one can be true. So here, this would result in a 0. Almost wrote a 1 because I was thinking 1, but that's going to result in a 0. Now we have our NOT gates, which are also known as inverters. I have my input and I have my output. Notice in this one, we only have one input going in, and that's because sometimes we only want to change one input rather than both inputs. Now, a NOT gate is also known as an inverter. It takes one input and will invert the value. If the value coming in is a 1, it will invert it to a 0, and if it's a 0, it will invert to a 1. So if my switch is off, once it comes all the way through this inverter, my 0 will change to a 1. If it's a 1 coming through this inverter, it will change it from a 1 to a 0. It is that easy. So this is our truth table for a NOT gate or inverter. Now we're moving on to a NOR gate. So it has the in front of the OR. So a NOT OR gate. And right here, you'll notice something that is new that's attached to a OR gate. We know this is an OR gate because it looks like that Star Trek symbol turned sideways. We see it has, you know, an inverter here. So what's going to happen is it's going to flip the value of that OR gate. Now, an OR gate is the opposite of an OR gate. There's an inverter on the end of the OR gate, which inverts the value. Now, I've added an extra column so you can actually see this. So here's our truth table. Right here is a column that I added. We're going to show our regular OR gate outcomes, and then what we're going to do is we're going to invert them or flip them. Here, this would be a 0 because A or B, not one of them is true. Here, B is true, A is not. Here, A is true, B is not. Here we have A or B, at least one of them is true. That will show up as a 1 there. Now, this inverter right over here is going to invert these values. So it goes through the OR gates, and then it's going to have a value of a 0 or a 1, and then it goes through the inverter and then gets inverted. That means when A and B are both 0 going through a NOR gate, it's going to show up as a 1. When B is true and A is not true, that's going to show up a value as a 1, but then the inverter flips it to a 0. And the same thing with these columns right here. So it goes to the OR gate, gets a value of a 0 or a 1, and then it will invert it. And that's why these 3 1s have become 0s in these 3 instances. Going through a NOR gate, the only time it should work is when A and B are both off. Now we have a NAND gate. So a NAND gate is the opposite of an AND gate. There is an inverter on the end of the AND gate, which inverts the value. And we've added an extra column here so you can see this. So here we have our regular AND gate. This is an optional column. You do not have to put it. So we have our 2 inputs. We have A, we have B. It's going through the AND gate, but then we have an inverter and it will give us an output. So when we look at our truth table, remember with an AND gate, both A and B have to be true. A and B are not true here. A and B are not true here. A and B are not true here. They are only true here, which results in a 1. But then after it goes through the AND gate, it's going to invert this. The 0, when both of them are off, gets inverted to a 1. This AND gate, when B is on, A is off, the 0 gets inverted to a 1. When A is on, B is off, this 0 gets inverted to a 1. When A and B are both on, this 1 gets inverted to a 0.